Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In today's class, we are going to discuss some of the advanced scheme for convection. As we have been seeing through the last few classes, we did the stability analysis, we did the modified partial differential equation analysis for many different schemes, mostly FTCS, FTBS, implicit approach, explicit approach and so on and so forth. We also did the error analysis and we looked at the dissipation error as well as dispersion error. And what we observed that there are some schemes which are stable, but they are highly dissipative, right. For example, FTBS. The schemes which are accurate, for example, FTCS are not stable, right. So, today we will look at some more schemes which basically tries to balance out these errors and also give you the stability. Okay. So, let us start the class today. So, this is our linear convection equation. Okay. These schemes that we will be discussing today is only for the convection equation, because you know that the diffusion schemes it already has that diffusion. Okay. So, that makes them stable, although there are from the stability analysis we see that there is a criteria nu delta T by del x square that has to be less than 0.5 for explicit scheme, but not that is normally not basically limiting point in our simulation. The limiting point in our simulation is basically C delta T by del x. Okay. And this has to be basically less than equal to 1 for FTBS, and this is the FTCS is unstable. Okay. So, that we know so far. Okay. Just a quick recap, this is our FTBS I minus 1. Okay. This is implicit but central scheme. Okay. So, this is n plus 1 and n plus 1, and you can see this is the central scheme I plus 1 and I plus 1, I minus 1. And similarly, we had the Crank-Nicolson, which is basically average between n and n plus 1. Okay. It is not I mean, instead of taking either n or n plus 1, you take n and n plus 1 and take the average of that. Okay. Now, before we get into more schemes which are basically more popular in the literature for solving convection problems, we see how they are derived. Okay. So, the best scheme that we know is the FTCS scheme. Okay. Forward in time in center and space, where you, if you want to get the derivative here. Okay. So, you take this I plus 1 and I minus 1, these 2 points. Okay. You can march from n to n plus 1, right. So, if you want to calculate ui n plus 1 here, you get the value ui minus 1 n and ui plus 1 n and also ui n. Okay. That ui n, ui plus 1 n, ui minus 1 n, and get the value there. Okay. And that will work for all the nodes. Okay. Let us say you have some here, so that will go like this. So, this will give you ui minus 1 n plus 1. Okay. This is ui n plus 1, and similarly you can have going like this and this. Okay. This is I plus 2. So, that will give you ui plus 1 n plus 1, right. So, when we did the analysis using the modified PD, we saw that this equation is nothing but a convection diffusion equation. Okay. And moreover, what we had is the diffusion term was negative. Okay, minus C square delta T by 2, and because of the negative diffusion, the scheme blows up very quickly. Okay. So, we also performed the stability analysis, and we found that our amplification factor is basically higher than 1, and that is why it is not dissipative and it is unconditionally unstable, right. Now, let us look at some advanced scheme which are basically derived on the FTCS scheme. So, what is our target? We want to use the characteristic of our FTCS scheme. Okay. That means, we do not want too much of dissipative error, but we want to make it stable, right. So, the first way to do it is done by Lax. So, Lax is a very famous mathematician, he proposed many schemes. Okay, we talked about Lax equivalence theorem, we will talk about Lax Van scheme and so many more schemes. So, this Lax-Frederick scheme, or is also called Lax scheme, okay, just also called Lax scheme. Okay. So, this is proposed by Peter Lax. So, Peter Lax is now I think 98 years old when you are talking in 2024, and is still alive, okay, and he has immense contribution to, in mathematics and linear algebra and development of this kind of schemes. Okay. So, what was his proposal is that so you have this scheme which is a central scheme, okay, minus C delta t by del x u I plus 1 and minus u I minus 1 n. Okay. So, said that replace this with the average of I plus 1 and I minus 1. Okay. So, then it becomes a Lax-Frederick scheme. So, why we do that? We will shortly see. If you do that, then the scheme becomes stable, right. So, the scheme will be y plus 1 u minus 1. This is what we are replacing the first term, and the rest all remains the same as this one, and this gives you the u I n plus 1. Okay. So, what are the nodes that are participating in the calculation of u I n plus 1? If you make our node, okay, this is I plus 1, this is I minus 1, this is n, and we are jumping to n plus 1, calculating at n plus 1. Okay. So, this, okay, let me write this is lambda by 2 u I plus 1 and minus u I minus 1 n. Okay. So, we want to get the value at this point, which is u I n plus 1, and to get that you get the values from I minus 1, okay, here, and I plus 1 here. So, this does not participate, okay, u I n does not participate. Okay. You are trying to calculate u I n plus 1, but u I n does not participate. Okay. Similarly, if you want to calculate u I plus 1 n plus 1, then u I plus 1 n will not participate. Okay. Now, let us look at the sum of the properties of this scheme. Okay. So, what we will do, we will go through our regular analysis. One is the modified PDE, another is the stability. Okay. Let us look at the stability first. Okay. So, u I n is equal to half u I plus 1 n plus u I minus 1 n minus lambda by 2 u I plus 1 n and u I minus 1 n. Right. So, I will not go into the detail, I will do it very fast. As we know, we are representing u I n as e to the power n e to the power I, okay, because psi is the index here, grid index. U I plus 1 will become e to the power n e to the power I plus 1 phi, right. So, if you use this value, okay, this is my n plus 1. So, this is e to the power n plus 1, e to the power n will come out everywhere, and this is half e to the power I phi plus e to the power minus I phi. So, basically I am taking this e to the power e I phi common on both the sides, the entire thing is multiplied by e to the power I phi. Okay. So, this is not phi, this is I phi and minus I phi. Okay. Capital I is the complex number square root of minus 1 and I is the grid index once again, so that there is no confusion. Okay. And minus lambda by 2 e to the power I phi minus e to the power minus I phi, right. So, we use the Euler equation. So, e to the power I phi plus e to the power minus I phi will be 2 cos I phi, 2 cos phi, right, because it is cos phi plus I sin phi, it is e to the power I phi, and if you subtract it, that will be 2 I sin phi, right. Use this value and take this g to the power n plus 1 by g to the power n, okay, and call this as G, this is the amplification factor. So, this will become cos phi, right, minus lambda I sin phi, right. So, how will it look, right. So, if you had a cos phi minus I sin phi, okay, then this is a circle, right. Remember the argon diagram, okay, circle of radius 1 and center 0 0, okay, in a complex plane. So, if this is your complex plane, this is your real versus imaginary, okay. So, this would become a circle, okay, do not make a very nice circle, but this is how it is, the radius is equal to 1. But what we have is G equal to cos phi minus I sin phi into lambda, right, that is what we have, okay, lambda I sin phi. So, now what will it be? This is an ellipse, okay, centered at, because there is nothing adding here. So, centered at 0 0, and the major axis will be the cos phi, the term multiplying the real number, that is major axis is 1 and minor axis is basically lambda, right. So, if you want to plot this, okay, so make this as 1, okay, let us say this is 1 and minus 1, okay, and take the value of lambda, let us say take lambda equal to 0.25, right. So, if this is your 0.25 and this is your 0.25, this is your ellipse, okay. If you have lambda equal to let us say 0.5, then let us say this is my 0.5 and 0.5, so this is another ellipse, okay, this is your, this is 0.25, this is 0.5, and if you have the value as equal to 1, okay, then that will be a complete circle, okay. This is lambda equal to 1, and if you have lambda greater than 1, let us say lambda equal to 1.25, then you will see that your this minor axis or the imaginary axis will become bigger, and that would become like this. Okay. Now, this is your 1.25 and this is your 1.25. Okay, sorry, the curve does not look very good, but I will show you the plot which I generated using MATLAB. Okay. So, you can see that for all the cases below 1, okay, take any point, that will be the your amplification factor. So, how do you get the amplification factor? So, G is basically square root of x square plus y square. So, from the origin draw a line, and you can see that anywhere up to 1. So, here the G is equal to 1 for lambda equal to 1, for all the cases G is less than 1. So, this is our region of stability, right. So, this is all our region of stability, okay. And if you go outside, okay, so if you take go outside anywhere beyond lambda equal to 1, then this is G is greater than 1. So, that is unstable. So, this scheme is stable for lambda less than 1, right. So, this is what we show for the less than equal to 1 for the lax Frederick scheme. Okay. Let me show you the plot that we got it here. Okay. This is what I was trying to draw. Okay. So, entire this region is our region of stability up to lambda equal to 1. So, this is lambda equal to 1 plot. Okay. So, this is all stable, and if you go beyond that, okay, lambda equal to 1.25, this is green circle, and if you take a line from this axis from the center, this is G is greater than 1. So, that is unstable, right. You can easily plot this using any tool like MATLAB or maybe Python, whatever is you are convenient with. Okay. Now, let us discuss a little bit about the other properties of this scheme, right. So, we want to do this modified PD analysis, okay, for this. So, that will be ui n in half ui plus 1 n plus ui minus 1 n and minus lambda by 2 ui plus 1 n minus ui minus 1 n. Okay. So, how we used to do MPD, if you recall. Okay. So, we will use the Taylor series for both time and space. Okay. So, if you do ui n plus 1, that will be ui n, and then you will have derivative with respect to time. So, delta t uti n plus delta t square by 2 utti n. Okay. And similarly, if you use this ui n plus 1 n, this is ui n plus delta x uxi n plus delta x square by 2 uxi n, okay, and so on and so forth, right. If you have ui minus 1 n, that is ui n minus delta x uxi plus delta x square by 2 uxxi n minus delta x square delta x cube by factorial 3, that is 6 uxxi n, and so on and so forth, right. So, this can be written as ui n plus delta t uti n plus delta t square by 2 utti n, okay, plus right hand side I will use another color. Okay. So, this if you add these two, okay, so what will happen, all these odd derivatives will cancel out and even will remain, right, and the 2 will cancel out with this 2, because ui n plus ui n, which that will become 2 ui n. So, you can write it as ui n, okay, this term I am doing, and plus delta x square by 2 uxxi n plus delta x to the power 4 by factorial 4. Okay. So, write factorial 4 uxxi n plus so on and so forth. Okay. Now, I will do this term lambda by 2. So, now instead of adding, we are subtracting. So, write lambda by 2 as c delta t by del x. Okay. So, c delta t by 2 delta x. Okay. And now, the odd derivatives will cancel out and even will remain, right. That and 2 is there, the 2 will cancel out all the, because you will add 2. So, this will become 2 delta x, that will cancel out by when you divide by 2. So, that will become delta x. So, let me remove this 2 here. So, this is delta x uxi n, okay, plus delta x cube by factorial 3, okay, uxxi n plus delta x to the power 5 by factorial 5 uxxxi and so on and so forth. Okay. This is minus sign. Okay. So, what we used to do now, so what we need to do, we need to write in a form which is basically ut plus u cux I is equal to something, right, and then we are trying to find out what is my leading truncation error. Okay. That will give us the modified PD equation. Okay. So, start so this ui n will cancel out, okay, and you have this delta t I will divide everywhere. So, this is uti n plus delta t by 2 utti n, okay, that will be this first term, if you can collect, that will be delta x square by 2 delta t uxxi n, okay, and then you have a higher other term, I am not writing those, okay, and here I am just writing the first term, okay. So, the delta x will cancel out. So, c uxi n, this is the first term, and possibly the second term also, minus c delta t delta x square. So, delta t will cancel out, okay. So, c delta x square by factorial 3, that is 6 uxxi, right, and then other terms, okay. Now, we will collect these two together. Okay, this is ut plus cux in. Okay, now start collecting similar order term. So, this is now delta x square by 2 delta t uxxi and minus delta t by 2 utti, okay, and minus other terms c delta square by 6 uxxxi and so on and so forth, right. Now, look at this term very closely. Okay. So, how did we convert the t to time derivative to the space derivative? So, you know this ut equal to minus ux, take second derivative, that will become c square uxx, right. This is the trick we have been using to get our first leading order term in terms of space derivative, right. So, you can write 1 by 2 delta x square by delta t minus this will become c square delta t uxxin, okay, where we convert this uttin into c square uxxin, right, minus c delta x square. Anyway, these terms that we are preserving is only space derivative and so on so forth, right. Now, this is an interesting scheme. Okay. So, if you look at this closely, delta x square by delta t minus c square delta t, okay, this is the term that we are trying to observe. So, this is my leading truncation error term, okay, and this is the diffusion term. Okay. This is the convection diffusion equation, but my leading truncation term is, you can put half here like this. Now, this is not always a consistent scheme. This is a very important thing to remember. This is not always a consistent scheme. Recall the definition of consistency, okay, as delta x tends to 0, delta t tends to 0, okay, your leading truncation error or all the truncations error rather should go to 0. That means, your finite difference equation should become the PDE exactly. Okay. If you look at this case, okay, if delta t goes to 0, this does not go to 0, right. So, the only way this scheme can become a consistent scheme is that when delta x tends to 0, delta t tends to 0, okay, when goes to 0, your delta x square by delta t should go to 0. Okay. So, this is a very important aspect that I want you to keep in mind, that for consistency of this scheme, your term delta x square by delta t should go to 0 as delta x goes to 0 and delta t goes to 0, right. So, if the scheme is consistent and stable, then only you will get the convergence, right. So, this you have to guarantee for consistency of this scheme. The other important observation that you could do is basically what you can do is maybe I will do this delta x by 2, okay, and this become, so I am writing this term delta x by delta t minus c square delta t. So, probably to take c also, c delta x by 2, okay. So, this will become delta x by c delta t and this is c delta t by delta x, okay. This is uxx in, okay. If you write it, this is c delta x by 2 and what is this? This is 1 by lambda, lambda is c delta t by del x minus lambda uxxin, right. So, this is our leading term in the convection diffusion equation, which is the modified PDE, right. So, the other interesting thing you can note that this is a highly diffusive scheme, right. Why it is highly diffusive or highly dissipative is because of the presence of this 1 by lambda term, right. So, let us say that for stability we know that we want lambda to be less than 1, right. So, if you take lambda equal to, let us say you take lambda equal to 0.1, very small value, okay, then 1 by lambda becomes 10, okay, and this coefficient of diffusive term becomes 9, okay. So, 1 by lambda is 10 minus 9.9. So, this is a very high dissipation value. Okay, typically you have delta x is y and so on and so forth. Here, because of the presence of this term, or maybe multiply by some lambda value, but because of presence of this term, you are getting a very high dissipation, which is coming because of the factor of 1 by lambda. So, that is why this lambda, this Lex-Frederick scheme is very highly dissipative, and I will show you some results with Lex-Frederick. In fact, I will show results with all the schemes, okay, that we are discussing, and compare with FTBS, FTCS and so on and so forth, right. So, if you choose a very small lambda value also, your dissipation is very high, and then you will get a value which is highly dissipative. So, if you are starting with this sine wave, okay, you will get a solution is like this. Okay. So, it is completely dissipated, right. So, this is another property of the Lex-Frederick scheme. So, if you want to use this scheme, you use the value which is as close to 1, okay, so that this 1 by lambda value does not go very high, okay, let us say 0.9 or 0.95 or so on and so forth. Okay. The other thing that you can check here is that our the order of a scheme. So, because of the fact that we approximated UIN with UI plus 1n and UI minus 1n, our scheme out of this the accuracy reduces to first order, which is delta t and delta x square by delta t, as we saw in the last slide when you look at the MPD. Okay, this one. Okay. This we already discussed, consistent only when delta x over delta t equals to 0, is stable for lambda less than 1, okay, and this has got a very high dissipation. So, these are some of the properties of the Lex-Frederick scheme. Okay. So, what we will do in the next class, we will look at some more schemes. We will look at schemes like leapfrog scheme, okay, and a very important scheme which is Lax-Van Dorf scheme. Okay. We have already, I think I have already given you a flavor about these schemes earlier, but I am going into detailed discussions now about the stability of these schemes and how these schemes behave, so or should behave. I will show you the solutions using these schemes for many different kind of problems in the next coming classes. Thank you very much. We will meet in the next class.